Okay, can you hear me? Can you hear me all right?
Yeah, you're good. Thank you.
Okay, we can go ahead and get started. Today we're going to be talking about ms08 and we're going to be looking at it from kind of a different angle. This is an older vulnerability. It's been out for 5 years now, and it's pretty popular. It's kind of well documented, but we're going to look at it from not so much as an attacker trying to get into a machine, or not so much vulnerable source code, but we're going to look at it, what it looks like on a target machine in a running environment. My name is John degruyter. I'm a Christian security researcher, a Marine Corps veteran. I'm also an adjunct professor at George Washington University, and I help run Capture the Flag with a few other guys. So if you haven't started yet, we have a few challenges that are available for download for HackerCon here. But I encourage you to play. We got, I think, like 15 challenges, all different types, all different skill sets. So definitely encourage you to give that a shot. So it's hard to see in the back, but how many of you have seen this before? Right? This is pretty common when you're learning Metasploit. It's basically what we were talking about, the ms08 067 net API module. And it attacks a vulnerability in Windows. How many of you have used Windbg before? All right, today we're going to be talking about, we're going to take a look at the Metasploit module itself, just an overview, so we can see like what's going on in the module, and we're going to use that to follow it on the target system. And we're going to look at it at a low level. Once we see kind of what it's attacking and where it's attacking, we're going to track down the vulnerable code. So we want to kind of pinpoint what's happening exactly. And then we're going to look at the memory corruption. We're going to launch the payload at the target system, and then we're going to watch the overflow. It's a stack-based buffer overflow. And then after that, once we have control of execution, we're going to see what it does next. And what that is, it's going to disable depth, and then it's going to jump to our shellcode. The setup's really simple. There's just 2 virtual machines. I got a target virtual machine that's Windows XP, 32-bit Service Pack 3, and the attack virtual machine is Backtrack running Metasploit. All right, so let's get a quick overview of the Metasploit module. There's 4 functions in it. It's the ms08 067 netapi.rb. That's the name of the module. It's written in Ruby, so you can just open up a text editor and kind of see what's going on inside there, but you'll see 4 main functions. Today we're not going to be talking about check, and we're not going to be talking about generate ROP. We're not going to have to use ROP on this particular target, so we're just going to avoid looking at that. The exploit section is what kind of pulls everything together and launches the attack. It sets up the SMB connection. It takes information from our initialize function, pieces it all together exactly where it needs to go, and then launches the payload, handles any thing that might be coming back. So that's really what does the meat. But the initialize function is interesting too. That has a bunch of metadata information. It has the author of the module, possibly the credit to whoever found the exploit, different CVEs that are related to it, and so forth. So a lot of interesting information in there. And then it also has a targets section. And that's important to us, the target section, because it gives us a little bit of information of what we want to look for on the machine that we're actually targeting. So this particular module, like I said, it's well put together. It was a popular exploit. It has 63 different available targets. So we have Windows 2000, XP, Service Pack 1, 2, 3, Windows 2003, and we have a bunch of other different languages. So there's a ton of different targets that this exploit works against. So why do you need 63 different targets to attack? Can't you just throw it and have it work against all of them? Well, it's important because the target section, this section here, the target section specifies exactly where you want to go. The target section can have different variables, but for this particular exploit, it's telling them where we want to go after we have control of the instruction pointer, or EIP. And those are slightly different for each of these targets. That's why we have multiple ones. For example, on the second to last, or the second one from the top, the RET address is 6F88F727, right? But the one we're looking at is 6F88F807. So it's slightly different for Windows XP Service Pack 2 than it is XP Service Pack 3. That's why we have multiple targets. Today we're going to be looking at target 6, which is XP Service Pack 3, English with NX. And our target specifies 3 different variables, and they're just memory addresses. We have a scratch address that is 20408. We have a RET address that I just read, 6F88F807. And we have a DisableNX, which is 6F8917C2. And we'll see those addresses again here shortly. Also in the module, in the comments, it talks about the vulnerability description. Now there's other places you can go to get information about the vulnerability. You can go look at CVEs or even write-ups. There's a lot of write-ups on this one in particular. But I was just going off what you saw in the module itself. And here it points out there's a problem with NetAPI32.dll. So that particular DLL is where the vulnerability exists. And it talks about it being used by the server service. So if we want to look at that on the target system, because that's our goal, to see what actually happens on the target system. So if we want to look at that, we want to track down where that code is. So NetAPI32, server, service, that's what we're looking for. We open up Task Manager, but Task Manager only gives us a list of processes. And the processes are designated by exe or image names. We see a lot of service host.exe, but we don't see server. We don't see our server service that we're trying to track down. So another thing we can do is use another tool, Process Explorer. Process Explorer is from the sysinternals tool suite. There's a lot you can do with this, and there's books on the sysinternal suite that you could buy. But the feature we're interested in is looking at the different services that are associated with a process. So if you just hover your mouse over the different processes, you can see a lot of information. And particularly, you can see the services associated with that process. And on the left, you can see that the server service is running with this particular process that I'm hovered over. And that's a service host.exe. Like I said, there's a lot of those. So it's important to get the PID, or the process ID. And the process ID gives us a specific number that's associated with that particular process, or that particular version of service host.exe that we see there. Okay, so we know what process we want to kind of pull apart and look at. But to get down even further, the Metasploit module tells us the vulnerable function. And that's net PR path canonicalized. Okay. And I wasn't sure how to pronounce that, but Iron Geek, the talk before this, said it about 100 times, so I think I got it pretty close. So now we want to find this function, okay? This function within that process. And to do that, we're going to use a debugger. Windbg is a pretty powerful debugger. There's a lot you can do with it. I started with OllyDebug and used Immunity, and now I'm trying out Windbg. And I like it so far. It's a little intimidating at first. You get basically one window starting out, but you can add in different windows and create the view you want. But the debugger is going to allow us to attach to the process and examine those different sections of memory and kind of drill down to that NetAPI32 DLL and drill down into that netpr path canonicalized function. So that's what we're going to use this for. And when we talk about debugging Microsoft products, we should talk about symbols. Symbols are helpful because they allow you to map a name to different parts of memory. For example, it's a lot easier to remember kernel 32 read file than it is to remember 767B9C31. So it just maps these human readable names to functions, variables, and things like that. And the way it typically works is you can point it to a Microsoft server, and when you break in the debugger and when you're looking at things in the debugger, if you don't have the symbols, it'll go out and download them for you kind of on the fly and associate the names with those addresses. So it's reaching out to Microsoft But with this particular process, with this service host.exe, that can be a problem because when we freeze it, that's the process that's involved in going out and fetching those symbols. So it's basically just going to hang the system. So to get around that, what you need to do is cache all the symbols locally before you start debugging. And you can do that with a tool like symcheck.exe. And if you Google Introduction to Symbols, MSDN has a really good brief introduction on that. So check that out. Okay, so let's kind of view what we're going through so far. All right, so this is Process Explorer. You can just hover over. Gives you the service names like we talked about, and we find the server service, right? So now we select that particular process, and we look at the PID. And the PID is important because it tells us which version of servicehost.exe that we want to attach to. And that, in this particular example, is 1020. And today's 1020. No, today's 1019, but it's a weird coincidence. So 1020 is the process ID that we want to attach to. All right, so once we know the process ID, let's see what else we can see. In Process Explorer, it gives you a preview pane at the bottom. And at that preview pane at the bottom, it's kind of cool because you can see different DLLs that are associated with it. So here we see netapi32.dll. So we know our vulnerable DLL is associated with the process, just as we expected. All right, so now we're ready to, one last thing, in the symbols directory, I'm just showing you here that I have a lot of PDB files already. And what I did was set up that C:\symbols as my cache. So I've pulled down all the symbols beforehand so that it's not going to hang when it tries to use this service and try to fetch symbols. So they're all there, and the netapi32 symbols are there as well. So that's the PDB for that. So now we're ready to kind of track it down in our debugger. So we use Windbg, 1020 service, we attach to this, and once we do that, it's going to give us a bunch of information, and then it's going to pause. So the service now is actually paused. And like I said, you can set this up how you want, so you can add these different windows in and kind of organize your view the way you want it. And it's kind of tricky to dock these things, but once you play around with it a little bit, you get it. But I'm trying to dock this at the bottom. So at the bottom here, I have a disassembly window, and that shows me the instructions of what's actually going on, the assembly instructions. And another window I add is the call stack. So these are the different functions, and we'll talk about why those are important later on. I'm also adding a window for the registers. So I'm just adding that in there and resizing it, and now I'm set up the way I want to work. So the first thing we can do is look for that module. So LM will list the different modules loaded in the process. And the modules are the DLLs. And with these DLLs loaded in memory, the process can use functions from these DLLs. So you know, it doesn't have to recreate the wheel every time. It can reuse something that's already been written. So LM just shows us information about that. You can use LMM to view a particular module. In this example, we're looking at the netapi32 module. And LMVM will give you verbose, and that'll give you even more information about a particular module. And when you do that, you get things like the start address of the module. So that's the start where it's loaded in memory, and the end address of the module. You get the file name, which are important, and we'll look at how we can use those later on. And the next thing is we want to find the function. So we know it's the netpr path canonicalized. So we can use the X command in Windbg to look for functions. And it takes wildcards too. So here we're searching the module goes on the left. So module, exclamation point, and then function. So here we're using a wildcard, so looking for any module that has netpr path in the name. So that's what we search for, and we find multiple entries with this. And looking at the search results, we actually are going to use server service to start out, because this is what initially gets called before our DLL gets called. And if we use U for this server service, it's going to unassemble it. So what that does is give us the assembly instructions for this particular function. So that's the beginning of the function, and these are the instructions that are going to run as soon as it gets hit. And we can also put this in the disassembly window. We have scope IP, but we can replace it with another address or another name and see it there as well. So that's it for the first demo. Now we have the vulnerable function that we want to look at. So now we want to look at the memory corruption itself. So we know what's possibly bad, so what actually happens. So when you're looking at this function, what it actually does is it sets up the stack with these push instructions, and it actually calls another function. You see that it calls netpw path canonicalize. And that eventually gets us into our netAPI 32 DLL, which holds that function. And these are just some of the commands. We just use the X to locate a function, and then the U to unassemble or look at the instructions. So here's our vulnerable function. And in the Metasploit module, it doesn't tell us which actual instruction, which memory offset has the vulnerable code. So we don't actually see where that's at. But we know what happens with stack-based buffer overflows. And what happens, there's a stored instruction pointer, and when we return to the calling function, that stored instruction pointer gets put into EIP, and then we begin execution from there. So if we can overwrite that stored instruction pointer and put what we want there, then we win. That's the kind of the essence of the stack-based buffer overflow. So we know that there's going to be a memory corruption, and that stored instruction pointer is going to be overwritten. So if we can see that happen somewhere in this function, then we know exactly where the vulnerability is. And you track this function down to the end, and you see this. This is WCS-CPY. It calls another function, and it calls it at offset hex 1FA. And what that means is from the base of that function, you go down 1FA and you see another call. In this call, it's going to cycle through once and it's going to work okay, but when it comes back and hits it the second time, that's when the memory corruption occurs. And the problem is we can manipulate the data so that what we copy in from the source to the destination is larger than what the destination can hold. So we're going to write past that bound of where we're supposed to be and overwrite the stored instruction pointer. And this is what that function looks like, the WCS-CPY, or the copy. Basically, it's a loop. We have our source, which is EDX, and our destination is pointed to by ECX. These are actually pointers to the source and destination. And then it just loops through. You see at the bottom, the JNE instruction goes to 77C47E9F, and that's what the red arrow at the upper left points to, 77C47E9F. So it's just going to loop back up to that instruction until it's finished with the copy. So this is going on as it's copying data. So what we can do is we can go into this function and set a breakpoint and then look at ECX and see what's stored there, and then loop through the copy and watch as the bytes get overwritten. And then eventually it'll overwrite our stored instruction pointer. And then when the function returns, it'll continue execution on whatever we specify with that overwrite. So it's going to overwrite stack data, our EBP, and then our stored EIP. And this is kind of what it looks like. We're going to do a demo as well, but this is after the corruption occurs. You notice at the bottom right pane in the stack frame, you just see addresses there. You don't see any symbols or you don't see any names besides AcGenral, right? Because it's been overwritten, it's corrupted. These don't point to valid addresses. So let's see a demo of what that looks like. If I can find it. Okay, so here's the next iteration. So we're going to attach to a process, and then I'm going to set up Windbg again the way I want to see it. I'm going to set up a disassembly window, put that in the bottom again. And then after that, I want to see the call stack. So I'm going to put that in the lower right. And then I want to add a memory window. So this is just looking at memory. And right now it's just on scope EIP, or scope IP, but I can specify what I want to put there. And I'm setting up registers as well, just for fun. So once I get all that squared away, how I want it to look, one thing to mention in this stack frame, it has different options you can use. So here I added, I wanted to show addresses. So beside the function names, I see the child EBP and the return address. And clicking headings shows that, just that, it shows the heading there as well. So what that means is this debug breakpoint, when it returns to the calling function, it's going to resume instruction at 7C950010. So that's where it's going to return and continue execution. So that's good to know for this particular example. And also I want to just view this top part in long hex so that I can see it as an address. And also the next thing I want to do, I have some breakpoints that I already have set up. So I can just copy and paste those in there. And BL will allow me to list my breakpoints. And the breakpoints I'm particularly interested in are the net PW path canonicalized plus hex 1FA, right? Because that's where it calls the copy. So on the second time it hits that breakpoint, then I want to jump into that function. And then I have two more breakpoints inside the copy, and the commands after those two breakpoints, BD1 and BD2, that's going to disable them. And I want to disable them because that particular instruction might get hit before I launch the exploit and before I'm ready to look at it. So I don't want to break on those until I know the memory corruption is about to occur. And then I have two more breakpoints, and these correspond to the variables we defined in our target. So one is 6F88F807, and that's a call ESI that's going to jump to our shellcode. And the other is 6F8917C2. And that's what we're going to overwrite the stored instruction pointer with. So once the breakpoints are set and everything's ready, I can just hit G for go, and that'll continue execution. So now it's running as it should normally. And switch over to the Metasploit VM and just type exploit, and when it attacks. So what's happened, we launched the payload at the service, and we've hit our breakpoint that we've defined, that we see where it calls the WCS CPY. So we're broke here, And if we continue, we just hit go again, and that's going to get us to the breakpoint a second time. And at that second time, we're going to use T that will allow us to step into the call. And once that happens, we're in the WCS CPY function. And this is what that looks like. So we have breakpoints here as well that we can enable that'll allow us to step through the loop and watch the actual memory corruption. So P will allow us to advance one step at a time, and you notice at the disassembly window at the bottom, it's just stepping through one instruction. So then what we want to do next is we have this memory window up here. So we want to use ECX, take the value pointed by an ECX, and put that in the memory window. And so we can, that's the destination. So we can watch the data from EDX being copied here. So we're going to grab that again and copy and paste it up in our memory window. So now we have, that's our destination. That's where it's going to begin to copy data. And then we can look at our breakpoints again, and we enabled our breakpoints for the loop, and then I can just hit G to go and continue to iterate through the loop. And as I do that, what we're looking for is this return address, 5B86A5A9. That's what we want to overwrite, because as long as that's there, we're going to return to the function that called it, the legitimate function that called it. So we want to overwrite that and return wherever we want. So you see it there, but it's also on the stack up here. So if we can write along that line and overwrite that address, it's a win for us. So we hit go, and you'll notice, if you can see it, the memory at the top is changing. So we're overwriting, iterating through that loop and overwriting our destination, as we should, but we also overwrite more than what we're supposed to because it's a buffer overflow, and this is due to the software vulnerability. And then we just overwrote part of our stored instruction pointer. And when we do that, we see that what happens is the address we were supposed to jump back to has changed. We have vproc image export directory, and that's just changed because we overwrote the first part of that, and it's beginning to corrupt the memory. So this is where the magic happens, and the next few writes, we can control that address that we're supposed to return to. And that's where it happens. So once that happens, we're telling it that we want to jump to AcGenral DisableNX. And that's the actual address we want to go to when this function returns, because that's going to enable us to turn off dep. But it keeps going, and you'll notice these symbol names that we have here. As it continues to overwrite the rest of the stack, all that stuff's going to get messed up. So those names aren't going to line up because we're putting different addresses on the stack. So you're not going to be able to actually see names associated with it. It's just data, it's just shellcode. Right, so that doesn't make any sense, and now we're kind of messed up if we want to return back normally because we've corrupted the data. But we are going to return to AcGenral DisableNX. All right. Okay, so now we've corrupted the memory. We've overwritten the stored instruction pointer, and we're jumping to a function, whatever function we want, and we specify that function in the target. So we're going to turn off dep, and dep stands for Data Execution Prevention. It's nice because you can see it in Process Explorer if you look at the properties of a process. I added a column here, but it tells you whether or not dep is on or off. And before we launch the exploit, dep is on, and after we launch it, it turns it off for the duration of as long as that process runs. So it'll remain off until you restart the process or restart the system. But dep prevents us from executing our shellcode. It's marked as non-executable, so it's just going to throw an error if we don't have. It's going to throw an error if we have dep turned on. So we want to turn that off first. And the way that we do that goes back to our target and why we have specific addresses in our target. So if you look at the AcGenral module with LMM AcGenral, it's a DLL that's loaded, and the start address is 6F880000, end address 6FA4A000. Well, something that's interesting that kind of confirms where we're at is that the RET and DisableNX addresses in our target fall within that address range. It says it there in the comment, but we can just verify it that we are actually jumping to addresses within this DLL. So the order we have to do it in is we have to disable NX or disable dep before we jump to our shellcode, and that's where we're going to redirect the control of execution. So if you do LMVM AcGenral module, you get some information about it. Again, you have the start address and end address, and you also have acgeneral.dll, and it shows you the exact path. That's useful because sometimes you may have DLLs in other directories with the same name, but this actually specifies which one you're using. So what else can you do with that file name? Well, another helpful piece about this module, it tells you how to manually go in and look for the DisableNX function within AcGenral DLL. And they suggest using a tool called msfpescan. And what that does is you can scan an executable .exe or .dll. You can scan an executable file and look for different patterns. So here they show us the function, what it looks like, push, LEA, push, 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 move, call. So those are the instructions here that are in this function. So it shows us that, and then it shows us the bytes we had to look for. So 6A048D45, we search for those in the DLL. And those bytes actually make up the assembly instruction. So if we search for those, we can find, and we have a match, we can find the offset of this function in the DLL. Now, why would you need to do that? You would need to do that if AcGenral would change. You know, maybe it gets patched or something like that, or maybe you're looking at it for a different target, a different service pack or operating system or whatever. But this is just a way to kind of find a function in a DLL. And you can search for it manually from within Windbg as well. So LMM and then the module name. So that gives us the start and end addresses for the module. And the search command is just S, and then you can give it D, and then a start address, which we use. We take the base of the module, and the end address, we use the end of the module, and search for the pattern of bytes, just like we did with msfpescan. And we do that, and it gives us an address 6F8917C2, which we've seen before, which is the address for turning off the NX bit, or turning off dep. And we see that push, LE, push, 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 move, call. We see those instructions again. And what we actually did, we searched for the byte pattern. So 6A048D45. If you look in the middle column, or the second column from the left, we see those same bytes, 6A048D4508. And those are the bytes that make up those assembly instructions. So that's what our search did, essentially gave us the location of this function. And we just do a U to unassemble that address, and we see the exact same thing we saw with msfpescan. Okay, shellcode. Most of the time, shellcode is generated with Metasploit. But there's other places you can get it, so you can download it manually and plug it in. You can modify existing shellcode if you're having problems on your target. This screenshot, you can use MSF payload and manually, or use this tool to generate shellcode from Metasploit payloads and kind of save it in a binary form. So that's where our shellcode comes from, and as most of us know, shellcode is just a way to kind of get a foothold on a system and execute what we want to execute and kind of gain further access. It's important to know where your shellcode will be. So at the time of memory corruption, where's your shellcode so that you can jump to it? And with this module, our shellcode ends up on the stack. And it's non-executable if dep's turned on. That's why we have to jump to the DisableNX function before we jump to our shellcode. In this module, our shellcode will be pointed to by ESI. So it may land at different addresses, but ESI will always hold the address where our shellcode is located. So if we can jump to ESI or call ESI, then we can get to our shellcode. But it's important to know where it's at. And in Windbg, you can do bang TEB to look at the thread environment block, and it'll tell you some information about the thread and show you the base address of the thread stack and the end address. And you can just verify that where your shellcode's at falls between that. And at the time of memory corruption, we can also do a search like we looked at before and kind of search the memory for that process and look for our shellcode manually, maybe if it doesn't fall in the right spot. And then getting to your shellcode. Well, we talked about the target. Well, that's what that ret is for, that ret address. We know ESI points to it, so we got to find a call or a jump ESI. So when the exploit function put everything together for us in Metasploit, it put this address in the payload and sent it off so that after the call to DisableNX, we would go to this call ESI instruction. And you can find instances of call ESI or jump ESI with tools like MSF-PE-scan, -J ESI, and then the module name, AcGenral.dll. So that's going to show us multiple places, if there are any, for us to get to ESI. And you see this tool was run, and the first call ESI, the address for that is what was used for ret. You can also do this with a tool called Mona. Mona is a Python plugin for immunity debugger. It's a great tool, but it's really good for finding jumps as well. And it'll give you some more information as whether or not ASLR is turned on or other helpful information like that. But ASLR is not an issue for us on this target. It stands for address space layout randomization, which would change the address where these static offsets are every time. And that's why we can use these static offsets, because they're not going to change. Anytime the DLL is loaded on this particular target, the call ESI is going to be here, and the DisableNX is going to be where it's supposed to be. Another thing we can do is manually search for instructions. So this is a trick that was taught to me by Brian Kavina. But while you're in the debugger, if you need an instruction, you can just assemble it there on the fly. So you can hit A, and you might want to do this at a different address. This example, I just do it, I overwrite EIP, but you can jump to a different address if you don't want the process to crash. But basically what I wanted to know is, what does a call ESI look like? What do the bytes that make that up look like? So you just hit A, type in call ESI, hit enter. I think you have to hit it twice actually, and you'll exit out of assembly mode. But that'll start to overwrite EIP with the instruction you wrote. So you can just do U EIP to unassemble it again, and you can see the bytes that make that up. So here it's FFD6. So now I have a quick way to find out that call ESI looks like FFD6 as far as the bytes go. And then I can use that search functionality again and search either a particular DLL or the whole process for call ESI. And that's what I do here, and it gives me a list of different locations where I see FFD6. So that's pretty much it. Once you get to the shellcode and DisableNX is turned off, you're free to execute it. So you get to the call ESI, that redirects you to your shellcode. You can execute your shellcode for a win. I just wanted to mention some Windbg resources. Windbg.info is an excellent site. It's really well organized to just kind of, if you're getting started, to give you the commands you need. OSR Online, they have some good forums there for figuring things out when debugging. There's also some very good training there as well. I took the kernel debugging and crash analysis course. It was an excellent class. I highly recommend it. Or in Windbg, just .hh or .hh, the command will give you help on a particular command. And these are just some instructions for caching the symbols locally before you start to debug. So what did we talk about today? We talked about an overview of the Metasploit module, different information we pulled from it, and then we looked at a target system, looked at the memory, tracked down the vulnerable code. We watched the actual memory corruption, and we watched it as it overwrote the stored instruction pointer, and then we had control, and we could point it wherever we want. Then we jumped to the DisableNX function and turned off dep, and then we went to a call ESI and then got to our shellcode. So that's all I have, unless there are any questions. Nope. Thank you.